Now we have the final talk of the session by Dhruba. He will be talking about radial transport in simulated disks.
Hello. Hello. Can you hear me? Okay. Hi. So, hi everyone. I'm Dhruba Chowdhury, and I'm a postdoc at Hebrew University, working with Avishai and Nir. And the work that I'm going to present is done in collaboration with them and also Omri, who gave a very nice talk. Okay, so unfortunately, Reinhard Genzel was supposed to be here and talk about his observations of radial transport, but he couldn't be here. So I'm going to briefly summarize his observational results, which is the motivation for my theoretical work. So this is a recent paper in 2023 by Reinhard Genzel looking at sort of 9 high redshift galaxies. So these are disk galaxies at redshifts of about 1 to 2. They are very massive and large, about sizes greater than 4 kiloparsecs. And what he's trying to do is sort of measure the level of radial inflow or radial transport of gas in these galaxies. So what you see here is the optical image of the galaxy, and then this is the map of the total line of sight velocity. So the total velocity would be a combination of the circular velocity and the radial velocity if there's an inflow. So then there's a model for the rotational velocity. So there's a model for the mass distribution in the galaxy. So you assume a dark matter halo, a bulge, a model for the disk, and then from that you get the rotational velocity. So you subtract the rotational velocity from what you measure on the line of sight, and that gives you the map of the residuals. And it's from this residual map that the radial velocity is inferred. Now, this is another map. This is the same map, but perhaps under a different method, so they look a bit different, but both of them are the residual map. This is much more easy to interpret than this one. But basically, what you do is that in this residual map, you draw a line, maybe take a line like this through the center, and then look for the maximum value of the residual in the magnitude, the maximum value of that in this direction here and in this direction. You average them and you get some value. So you do that along different lines through the center, and you come up with different values, and you pick the one which has the maximum value. So this method is called the maximum gradient method. So that gives you a level of or a magnitude for the amount of inflow. So in this map, you have about plus minus 50 velocity residual, so meaning that the inflow velocity is about 50 kilometers per second. This is another example, and just want to highlight that if the inflow velocity field, if the radial velocity field, if that is axisymmetric, then it can be shown that the maximum would be obtained along the minor axis. So you would have this funnel-shaped structure about the minor axis, and that is what you see in both these cases. Okay. And the absolute values for the 9 different galaxies that is shown here, the absolute values for the radial velocity. Now, last week, those of you who were present in the pre-conference workshop last week, Omri gave a very nice talk summarizing different theoretical models for radial inflow. So basically, there are naturally occurring physical processes that drive transport of mass inwards, and while the disk is maintained at marginal instability, so about Q equal to 1, so it can be turbulent viscosity, so the turbulence that induces torques, and in that case, the radial velocity, the inflow velocity is this. Can be torques driven by spiral arms, and this was shown by Krumholz and Burkett, 2010. So there can be torques that are driven by spiral arms in the galaxy. So Avishai showed this in 2021. So you get a different value for the radial velocity, but and somewhat different scaling as well. So there can be encounters between the clumps and the disks, again shown by Decalsari and Severino 2009, and for dynamical friction on the torques, dynamical friction on the clumps that can also drive inward migration of the clumps. So you get somewhat different scaling and also somewhat different values. But in all of these cases, the model predicts that there would be a mass inflow. Now, we can compare this to Genzel's observations. Right? So Genzel has these observations for 9 different galaxies, and what is shown with the different lines here are these different models. There are 4 models that I talked about, and then in the Krumholtz and Burkett 2010, with a different parameterization for the energy dissipation of how the turbulence decays, a different rate for the dissipation of turbulence, that gives a different model, that is Krumholtz 2018. So in all, you have 5 different models and the data points from Genzel. So this plot is with Q equal to 1. So see, there is these ones don't agree that much, but these ones agree pretty well. And again, you can also look at Q equal to 0.67, the reason being that for thick disks, the marginal stability is somewhat less than 1, as shown by Goldrich and Lindenbell in 1965. So it's about Q equal to 0.7. So if you take that, then the observed data pretty much sort of lies in line with the theoretical models. So this is very good. So we can go home. But this talk is about simulations. So now I want to talk about what we see in simulations. So I want to talk about the Vela simulations. So these are simulations of, these are zoom-in cosmological hydrodynamical simulations. So we have about 35 Vela galaxies, 34 Vela galaxies. And I'm just showing you one example of a particular snapshot from one of the Vela galaxies. So this is the 2D surface density map. So you see this sort of, and I'm only looking at the cold component, by which I mean the cold gas, the gas that is less than 10 to the 4 Kelvin, and young stars. So the stars which at ages less than 100 megayear. So you see the density map for this cold component, and this is the 2D radial velocity map. And this is averaged over minus HD to plus HD, so mass weighted averaged in that region. Now you see that there is this stream that comes in, and this is correlated with this negative radial velocity that is being observed here. And then here, this stream sort of starts to go outwards here, the motion of the stream here, and that is correlated with this red stuff here. And there is another stream that comes in from here, and that is correlated with this blue inflowing material here. Right? So what I want to highlight is that both the surface density map and the radial velocity map, it's highly non-axis symmetric. Right? So it's very, very non-axis symmetric. So we look at all the 34 different Vela galaxies, and from there we select disks. So we have a criterion for selecting disk galaxies. So there are about 1184 snapshots in total, and the halo masses, they range from 10 to 11 to 12 at z equal to 2. So what we do is we select large galaxies. So we have a cutoff in RD by HD, so the disk size by the scale length of the disk. And we select galaxies that are greater than 3, or snapshots that are greater than 3. And then we also do a selection in V over sigma, so requiring that V over sigma is greater than 1, so meaning that they're all rotation supported. V over sigma is greater than 1 at all radii. So this, by the way, what is plotted here is the average V over sigma. So that's why you see that there are some blue points here that don't get selected. So the selected ones are orange. So the blue ones that don't get selected have an average V over sigma that is greater than 1, but maybe it's not greater than 1 at all radii, so therefore they don't get selected. But it makes very little difference whether I select them or don't select them. So then what we can do is, from the map that I showed you, for all our selected disks, what we can do is we can measure the radial velocity in annulize, centered here. So on center, we can measure the radial velocity in annulize, and then we can also measure the disk average radial velocity averaging over the entire disk. So what is shown here is the disk average radial velocity. So what is plotted on the y-axis is VR over V naught. On the x-axis, it is V naught over sigma. So these two panels are the same. So the points in these two panels are the same. So you see the result from all the different snapshots, and then it is compared with the theoretical models. So here we have the models for q equal to 1, and here we have models for q equal to 0.67. The black lines and error bars here, these are just the median and the 1 sigma variation. So see that the theoretical models, they do not agree well with the simulated data. There's very little match between the 0.71s and the data. Even for q equal to 1, only it is sort of this model, which is the torques driven by spiral arms. So the Deckel 2021 agrees somewhat, the other ones not so much. And also I want to highlight that in some cases, we do find positive disk average radial velocities. So that happens in about 20% of the cases, which is not predicted by the model. So the models always give inflows and not outflows. Now here we just look at the correlation with the cold fraction. So this is the fraction of the mass which is in the cold component, and there is some correlation with cold fraction. It does increase as we increase the cold fraction. There is not much correlation with redshift. Now, what I showed you previously was the disk average radial velocity, and maybe we got low values because we averaged over the entire disk. So we can also look at what happens at different annuli. So I'm just showing you 4 different annuli. Again, the points here are results from the simulations, and the lines are the different theoretical models. And again, we don't see, so there is, first of all, from the simulations, there is some difference. So as we go to larger annuli, or further out in the disk, we do see somewhat higher radial velocities, somewhat higher levels of inflow, and the scatter also increases. But then there's not much match when we compare the theoretical models, except again the Deckel 2021 model. The other ones don't agree that much. Again, we can look at the correlation with gas fraction, and we do see some correlation with gas fraction, not much correlation with redshift. So now I want to talk about how to interpret Genzel's observation. So until now I was talking about the disk average radial velocities in different annuli, but that is not what we measure. So what we measure is what we see along the line of sight. So what is shown here is again one particular example. So you see the 2D surface density map here, the radial velocity map here, and I want to first talk about this figure and then come back to these two figures. So what we do is along different line of sight, so that is what is theta. So theta can vary from 0 to 180 degree. So in different directions, what we calculate is, so we take the projected field, so we have VR, so we take VR cos theta. So we actually take VR mod cos theta because we want to preserve the sign of VR. So we want to know whether it's an inflow or outflow. So that information gets lost if we do VR cos theta. So we want to have that information, so we take VR mod cos theta. And then what we can do is one of the methods, we can just mass average over VR mod cos theta. So if we mass average that, then we get some signal, and that signal is shown by the solid green line here, right, as a function of theta. And then the other thing that we can do is something similar to what Reinhardt does. So we can measure the maximum gradient. So again, in a given direction, we can look for the maximum on both sides. So we take, for a given direction or a given projection, we pick a line, we take the maximum on this side, the maximum on that side, we average them. We do that for different lines, and we get a value, which we call the maximum gradient. And we can also plot that as a function of theta. So that is shown with this dashed green curve here. The magenta curve, that is the mass average signal from the entire disk. So in this particular case, the magenta curve, that gives about a value of about 0.05. Right? So that's pretty low. And then if you look at the variation in the mass average signal as a function of line of sight, it can give somewhat higher values in certain directions, but still pretty low. We do get higher levels of signals when we look at the signal that is measured with this maximum gradient method. Right? So for example, in this direction, if you're looking here, so this is somewhere here, so then we get a high value, and this high value is consistent with this large inflow that is observed here. Right? So this is VR cos theta. These are maps for VR cos theta. So this large blue thing becomes red here. Right? That's just because of a line of sight projection. But this is the reason why you see this high value. And then, for example, in this direction, this is somewhere like here, you do have an inflow here, but that is compensated by an outflow here, so we don't get as much high value. So there is a variation with line of sight. We can also look at another example. This is another example. And again, the mass average signal is pretty small. It's about 0.02, so 2% of the rotational velocity. The mass average signal in different directions, that is also not that large, but you do get a high signal from this maximum gradient method. And in this direction, or sort of up to here, you get a positive signal. And this positive signal comes from, this is where you get a negative signal. So this theta is greater than 90, so this is here. So you're going to get a negative signal. So this is consistent with the inflow that you see in this direction. So you have a large inflow here, large inflow here. So this is what you observe here. Whereas if you're observing in this direction, so you have outflow in this direction, right? So this red outflow, and that is what you observe here. So depending on the direction, you can get both outflows and inflows. So now we can look at the comparison to Genzel's observations. So these are again the data points from Genzel. So here in this panel, the top panel, I'm showing you the simulation data points, and this is looking at the disk average signal. So the disk average signal is very small, and we saw that earlier as well. It doesn't agree with the data. But if you remember, the theoretical lines with Q equal to 0.7, that pretty much falls through these lines, right? It doesn't agree with the simulations, but the theoretical lines fall through here. And that we now think that it's probably a coincidence that the theoretical lines are just falling through here because it doesn't agree with the simulations. Next, you can look at what happens with this mass average signal along different directions. Again, that is pretty small, almost of the same level, and doesn't agree with the data. What agrees with the data is when we measure the signal using this maximum gradient method. So we are really picking up the high velocities. And since in Genzel's observations, although what he measures is always interpreted as inflow, but it's hard to say whether it's an inflow or an outflow, right? Because it will give you the same signal along the line of sight. So we also show our theoretical data points here because we get outflows and inflows from the simulations, and the data pretty much agrees with what he measures. We can also see the agreement with gas fraction. So Genzel has measurements of gas fraction. He also has measurements of redshift, and again, the data pretty much lies in the region of the observations. So let me summarize my results. So the typical disk-averaged radial velocity that we see in the Vela simulations is about 5% or less. A certain fraction of them is outflows. In comparison, the theoretical transport models, they predict larger levels of radial transport, about 0.1 or 0.2. Now, why does this happen? Why do we not see an agreement with the theoretical models? Maybe it's the deviation from axis symmetry. So maybe it's because of the highly non-axisymmetric velocity fields that we see. This is yet to be understood. So maybe it's because turbulence is not driven by radial transport, and as Andy talked about, maybe its self-regulation is driven by supernova feedback. Maybe it's driven by accretion, as Omri talked about, and that is not present in these models. So we need to understand why there's a discrepancy between the simulations and the models. The observations are in the ballpark of the theoretical estimates, but maybe it's just a coincidence. The simulated values do agree with observations when we do this maximum gradient method. at least along certain line of sights. So I'll end here and take questions. Thank you.
Thanks for the nice talk. I think there are these two processes. The radial transport is driven by, let's say, gravitational torques. That depends on how many filaments you have, how many spiral arms you have, whether you have a bar. But these structures do not really know how much energy I need to drive my turbulence. It's a completely different process. So if we bring it together, we somehow hope that we get enough potential energy release to drive the turbulence we need, but it's not what the galaxy cares about. So I think we need to really look into these questions. What kind of features do we generate if we have certain instability, and how much basically torques these features generate, and then we can really compare.
Right, so I did start looking at the talks. I don't have results yet, but we can talk about that.
I myself have comments that from our local universe experience, it's quite hard to derive radial velocity by fitting the velocity field because of the noise and particularly because of the degeneracy between the inclination and different velocity components. And actually, we had some literature before showing the method used in Ganser's work actually does not work.
Sorry, you say that it doesn't work?
Yeah, the method does not work in recovering the VR through simple mock tests, even without.
So you have already done that test, and
yeah, in the nearby universe, there are quite some literature about that.
Andy has
I have been talking to protoplanetary disk people, and they say that they can get a strong radial inflow through winds. So basically, they have magnetically driven winds, and the winds actually transport away a lot of angular momentum. And through that process, you can drive strong radial flows inwards. So maybe that's one way to generate this.
Okay, we thank Dhruba and we thank all speakers of the session. And I think the